Hi and welcome to video 7 on this video series on graph theory. It is for general maths in year 12, unit 4, topic 2. And I'm going to talk to you today about weighted graphs. Not a big topic, and it does come back a little bit later on in the unit. But for now, here's a graph with vertices. I've left one out, let's call this G. A, B, C, D, E, F, G. And they've got values on each of the edges. They're called weightings. Now, the obvious meaning of the values is that A, B, C, D, and A, B, C, D, E, F, and G are geographical locations, towns or something like that, and the weightings are distances. That's the obvious one. But it could be anything. It could be pipelines and costs to lay them, or the amount of water that could flow through those pipelines. It could be the cost of internet and internet services between those places. There's lots of different things it could be. But we're just dealing with the maths behind it and maybe occasionally dealing with the context. So if I want to go from A to, let's say C, I want to get from A to C, these weighted graphs can cause us to have to deal with shortest or cheapest path kind of problems. There's a really famous one called the travelling salesperson to do with distances. There's not really an easy way to deal with these graphs, but let's say I want to get from A to C and I want to do it in the most cost-effective way. There is a good way to deal with that. The hard one is to deal with how to get from A to every single location and make it as cheap as possible. That's a bit harder, but let's say I want to get from A to C. What I can do is I can look at the quickest or cheapest way to get from A to each subsequent vertex as I go on my way to C. So from A to G, I can do that in 5, and from A to F I can do that in 2. Now I might still be able to get to G a different way and cheaper than 5, so I might have to remove that. But I can see that I can get to E in 4, 2 and 2, and I'm not going to beat that because I've got nothing else, so even 5 plus 3 doesn't beat that. And A to D looks like 8, and if I go A, F, E, D, that's still 8, so that's going to be the best way for me to get there. Now A to B, it looks like 6. If I go A to E, which is 4, then I still can't beat the B to 6. And if I go from A, G, B to C, that's a 13. So I've got a 13 option there. But if I go A, F, E, E the cheapest was 4, plus that 5, I can get there in 9, so 13's out. There are other options. I could go via D as well. Remember, C is connected to B, E and D, so I'm looking for the cheapest ways to get to B, E and D. D looks like 8. I don't think I could beat 8. And if I travel along this 4, I get 12. So 9 is a winner. And the shortest path is A, F, E, C. And we write that down as A, F, E, C. For this particular exercise and stage in the topic, you're really just going to be asked to do things like evaluate the weighting of this path, perhaps, or maybe deal with the shortest path problem in a fairly simple context like that. But having a look at each of the vertices and the cheapest way to get to those is usually the best way to just process through the graph. Anyway, that's about it for weighted graphs. As long as you have the decent understanding of vertices and edges in graph theory, then the graphs is not a big step up, the weighted graphs, and then dealing with context depending on what the weightings mean. All the best.